Is James Abello from DIMACS, who will speak about the majority rule and combinatorial geometry via the symmetric.
Okay, thank you for coming. What I have done is I have made these from first principles. Some people that have had the patience to listen to me privately. I was tempted by a talk given a couple of weeks ago about the majority rule, some aspects of elections and things of that sort. So that's why I decided to prepare this talk to bring this to your attention. There are three pieces. First, what the majority rule has to do with the Weak Bruhat Order and what is the Bruhat Order. Then, from the Weak Bruhat Order, we create some class of graphs that appears to be a new class of graphs. Part 3, I will give you a geometric interpretation of those graphs, which is also a new result. So what is the apparent problem with the majority rule is that you are going to have a collection of linear orders written in one-line notation, and you would like to apply the majority rule to that. What that means that you are going to create the graph, the endpoints. So each of these guys is a permutation in the symmetric group. So you are going to take the numbers from 1 to n, and you are going to count the position of I versus j in these permutations. And you just count. It's I before j, you count how many times. And it could be that the number of times that I is before j is more than the number of times that j is before I. Then you put an arrow. That is the process. So 230 years ago, there is this guy called Marquis du Condorcet, and he noticed that it could happen that the majority prefer I to j, the majority prefer j to k, but that this is not the case. I prefer j by majority, j prefers k by majority, but I does not prefer k. That's called the intransitivity of the majority. So why this happened? So combinatorially this happened is because of this. You will find inside the set of permutations, suppose that you find 3 of them, such that x is before y, before z, but y is before z, before x, and c is before x, before y. And what is this animal? Well, that animal is a 3 by 3 lattice square. Right? If you put those 3 symbols together, so if you play the majority on these 3 guys, you will find a cycle. Because x beats y twice, y beats c twice, but c beats x. Right? So this, if you play the majority, gives you a directed cycle. That is the bad aspect. So actually, Kenneth Arrow asked this question when I was a graduate student. He said it would be interesting to look at the collection of permutations such that for no 3 symbols this happens. You have to take S, Y, C, P, Q, R, all of them. And for any 3 symbols, you don't want that to happen. Is the question clear? largest collection of permutations, so that for no triple of symbols, you have the 3 by 3 lattice. I call those sets consistent sets. So there were lots of constructions. So here is one example. I don't expect you to read that, and it's very blurry. And I did it like that because it was very blurry at the time. And I hope by the end of the talk, you will look at this and say, aha, that blurry thing is not that bad. Actually, there is a lot of structure here. This set is a subset of the symmetric group of 6 symbols. Does not contain a 3 by 3 Latin square, no matter what triple you pick up. And moreover, it's maximal. Maximal in the sense that you pick up any other permutation, and you try to put it in, to add it to this set, it will create a Latin square. So this is maximal.
And who found this first?
I don't know who found it first. I look at it second. So there were other conjectures. People were coming with these sets of certain sizes. They were maximal, etc. Now, so let's look at this problem from first principles. Here you have a set. Instead of going to A6, let's look at this for A4. A4 is just a subset of permutations on S4. Here is a set. The question is how many possible induced Latin squares you could have 3 by 3. Well, there are n choose 3 triples, right? N choose 3 sets, and for each triple you have this cycle. So no matter, you take the whole symmetric group and you do it, you are not going to find more than six times how many triples you have, and no more. So you come to me and you give me this set, and you want to check if there is a 3 by 3 Latin square from first principles. Well, you go and start looking at all the triples. 1, 2, 3, 4 has 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4. Look at the next one and start filling this in, checking. Is there or not? If at the end of the day, you look at now any of these, and happens to be that at least one of them is out, this guy is out, he's not there. This guy is out, he's not there. This guy is out, he's not there. The green guys are not there. So then you say, oh, that set is consistent. There are no 3 by 3 Latin squares. There's no more to it, right? The problem is find for any n maximal consistent sets. If you were going to do this, it would take some time. So that is the problem. Is the problem clear? I will be very happy by the end of this talk. This is exactly from first principles. I'm trying to do this at high school level. So the question is, we would like some way to organize the symmetric group in such a manner that this local aspect of these 3 by 3 Latin squares come out to the surface very easily. So this is an organization of the symmetric group on 3 symbols. Here is the identity. Here is the identity reversed in one line notation. This graph, you flip 2 elements if they are adjacent and they are not inverted. Flip 1, 2, you get 2, 1, 3. Flip 1, 3, you get 3, 1. Flip 2, 3, you get 3, 2, 1. Do the same thing here. Right? This is called the Weak Bruhat Order. It's just a name for something that you know. This is the Cayley graph. It's called the Cayley graph I'm trying to do this at the high school level. So there's a guy called Cayley. There's something called Cayley graph that are a way to order the symmetric group in this manner. And the only operation you are allowed to do is to flip pair of adjacent symbols. If they are in the correct order, you flip them. They have to be together. You cannot do anything else. Is that clear?
And by the way, is there a strong Bruhat order?
Yes, there is a strong Bruhat order in which you are allowed to jump. You may flip 1 and 3. They are in order and you can
adjacent.
jump.
They have to be adjacent.
They don't have to be adjacent for the strong.
Yeah.
Right?
Yeah.
So the strong has more
Yeah.
edges.
Yeah, more, yeah.
That doesn't work with this problem. It must be weak. If you do the strong, it doesn't do the job. It must be weak. It must be this. So if you look at this in this way, where are the 3 by 3 Latin squares? Like this, this. And this, that. There's no more to it. Now, what is the largest possible set that does not contain either this or that? Well, you are forced to do this. If you take this, well, you are good. All that. There's another one, which is you may take these two and take the parallel one, this H and parallel. Well, in this case, so the largest possible consistent set, it could be an assignment in high school, is 4. And it's maximal, and it's maximum. So this is a maximal set, which is maximum. So the first natural question is every maximal set maximum? The answer is no. This is not really general. So something more has to happen. Okay, now if we go to S4, and we do the same thing that I explained to you, you get this beautiful object. Happens to be that the Weak Bruhat order of Sn can be embedded in Rn minus 1. In this case, this is S4. It's embedded into R3. And there are explicit ways to find the coordinates of these points. So, this is the whole symmetric group, and this happens in general. I would like to say a couple of things about this picture. This is a beautiful object. This is a Cayley graph. This is what is called a Coxeter group. This is a lattice. This is a Rankel lattice. All the paths from here to the identity reverse have the same length. And there is something even more fascinating about this. Is that if you look at the maximal paths from the identity to the identity reverse, so you are allowed to walk all the time, going down, you are not allowed to move back. This is what is called a maximal chain in the Weak Bruhat order, the saturated path from here to here. There is something very nice. Take any such path and take any other such path. There are many of these maximal chains. There is a way to move from one maximal chain to another maximal chain in any dimension, not just in S4, in any dimension, by 2 types of moves. And these 2 types of moves can be described very easily. Let me look at this particular one. Happens to be that these quadrilaterals are formed when you switch a pair of elements and then you switch another pair of elements and they are disjoint. Here you flip 1, 2, and here you flip 3, 4. That's what forms a quadrilateral, because you can go that way, or you can go first that way, flip 3, 4, and then flip 1, 2. So that's a quadrilateral move. Coxeter, people refer to this as type 1 move. That's what it is. There's no more to it. There is another type of move. It's when you have things of this type. So you have hexagons. As you can see, you have hexagons. And this is true in any dimension. So anytime that you have a hexagon like this, you can take that piece and replace it by the other piece in the hexagon. So if you have this part, you can take this one and replace it by that one to get another maximal chain. Is that completely clear? So Coxeter proved any two maximal chains under the Weak Bruhat order. It was not called that way at that time, but he proved that you can move from one to the other by using quadrilateral moves or hexagonal. Is that completely clear? Okay, with that now, we can take this set that we started at the beginning, and you look at that set that I showed you, and happens to be that that set contains a maximal chain. So that set that I gave you, you look at it, and it has a maximal chain. Is that clear? But there is something even more interesting than that. What is more interesting than that is that what we found is some chain in that set, and now you look at the triples of that chain. Remember, you take every permutation here and you look at all the triples, and you just throw all of those into one set. Happens to be that that set of triples is equal to the set of triples of S. So if you want to think about what a maximal chain is doing, the maximal chain is consuming all the triples that a consistent set that contains that chain may have. Another way to think about it, if you look at the maximal chain and you go and look at these 3 by 3 Latin squares and you put check marks, when you finish the maximal chain, you have consumed all the triples. So what that means is that any other permutation which is not in the maximal chain. So what this means is, if P is in S but is not in the maximal chain, then the triples of P, what? What is it I have said? Are contained in the triples of S. What this means is this is a closure operator. I.e., out of this big set, from the consistency point of view, if you just locate the maximal chain, that's what determines the existence or not of 3 by 3 lattice. Okay, but this chain, this set may be very small. And if you go and look at the set that I showed you, that set is not just this chain, it has other stuff. What is the other stuff? Well, this is a symmetric group, right? This is a gigantic soccer ball, and you just found a thin hair. And there is a whole bunch of other stuff. Where is it? Maybe here? Maybe there? But the beauty of this is that they are not too far. Given the maximal chain, all the other elements that contain triples of that maximal chain are very close. So in this particular case, you take this maximal chain, and now you look at where are the other guys that don't bring any new triples, they are close by. And what close by means? Close by means that you can go from that chain to other chains containing those elements by using only quadrilateral moves. That's the theorem. So, abstractly, what we are saying is, if here you have some permutation which is not there must be some chain, you know how, but I can go from here to here only by using quadrilaterals. No more. If you use the hexagonal move, boom, that brings in immediately 3 by 3 lattice squares. Okay, so this graph theoretical depiction of this, and this is true in any dimension, can be mathematized, can be written in certain ways. But let me just remember that set that I showed you, that I said was very blurry. You can go and look at this in this way, and let me just give you an idea so that you understand how the proof goes. Those symbols that you have on top are nothing else than the transpositions that you use to go from the identity to the identity reverse. So that first set that you have there is a description of a maximal chain. And this contains all the elements of the proof. So what I'm saying is, here you have, in this case, this is S6. So you write down here the identity, and here you write down the identity reverse. This encoding there tells you how you go from here to here. First one says 4, 5. This is flip 4, 5. Next one says 4, 6. Flip 4, 6. Is that clear? So those are the n squared steps that you will have to make to go from here to here. Okay? So that's an encoding of the maximal chain. Now, it happens to be that now you start following those steps, and you start noticing.
Is that n choose 2 steps, right?
N choose 2.
Yeah.
What did I say?
N square?
Order n square. It's really n choose 2. Thank you so much. And you start noticing this. Look at this. 2, 3, 2, 3, 2, 3. So 2, 3 is sort of fixed there. Now, if you take that, and now you flip 2, 3 here, 2, 3 here, 2, 3 here, you obtain this set. And if you flip here 2, 5, 2, 5, you obtain this set. What I'm trying to tell you is that this picture is an organization of that crazy, blurry set. And all it happens is there are blocks, and each block contains certain pairs of elements that are invariant. 2, 3, 2, 3, 2, 3. And when you flip all of them in parallel, you get another set. Now you continue, you will find another block. This one, what is invariant here? 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3. So you, in parallel, change all of them. In this one, there is an invariant here. Not that one, but here is 2, 5, 2, 5. Change these two in parallel. In this other set, there should be some invariant. I painted for you. 1, 5, 1, 5, 1, 5, 1, 5. In parallel, now just this piece, and you get this. And here you find some piece that is invariant, 5, 1, 5, 1. You flip the 2, and you get that. And at the end, there is another. You continue in this way, again, there are blocks, there are invariants, you project them. This block, 3, 5. That block, 3, 6. This sub-block, 3, 4. This sub-block, 5, 6, etc. These invariants are precisely what you start with. So that crazy set that look very, very complicated can be described abstractly as follows. You have something, you find some invariant, some piece here that has some invariant, you project down by that invariant, and now you find this piece here. Now you attach this to the original set. You find another invariant set, you project, and now you find some other piece, you attach that to your set, and you iterate. So this is an algorithm to do this. And the algorithm is efficient. Now you will say, what do you mean it's efficient? How big these things could be? Well, these things could be exponential, but efficiency here means on the size of the output. I.e. is output sensitive. So that's the iterative subset projection. And let's summarize what we have said in this first part, is that these consistent sets, there are some nice structure. Those nice superstructures are changing the Weak Bruhat order. You take any subset of the symmetric group, you can define a closure operator on that set by looking at all permutations whose triples are contained in the triples of the set. And this may have some other applications in other branches. If this particular set happens to be a maximal chain, the closure of that maximal chain has this beautiful structure, and mathematically this means, what I described to you here, mathematically it means that that set is what is called an upper semimodular sublattice of the Weak Bruhat order. In fact, today, recently some people proved that this is really a distributive sublattice. But this means what I showed you in those pictures. What about the sizes? Well, some of these sets may be very tiny, like a hair, but they may grow to be very big. So the lower bound is n-2, but the upper bound could be as big as the Catalan number. And how you?
Examples of the extreme?
Yes, an example. That's a fantastic question. And when people ask fantastic questions, I give them some prize. I'm sorry. You deserve the prize. That's a good question. So I usually measure the effect of the talk by how many of these I distribute. So I still have more. Very good. Okay, so yes, there are such examples, but these examples are in very low dimension n. And when n tends to infinity, this is really a bad bound. So the answer to this problem is really between is 2n and 4 to the n, but really closer to the n. That's still answer. But this is the most general bound that we could prove. Is this clear? So this is an algorithm, this is experimental mathematics. What is then the open question? Well, can you find consistent sets that are larger to what I described to you? What I described to you is take a maximal chain, apply my algorithm, and sometimes I give you a huge set, sometimes I give you a tiny set. All the known sets that are maximum, and for each of them you need a paper to prove that it's maximum, all of them fit this. Nobody has shown a maximum set for n greater than or equal, for n greater than 6 that is not of this type. So the conjecture, are there any others that are bigger than these ones? Okay, I finished part 1. Do you have questions, comments, improvements? No. Okay, so that means it was very clear. Right, Eddie?
Yes.
Okay. So now let's go to graphs. How are we going to get graphs from this? So what we are going to do is we are going to take a maximal chain. Why maximal chain? Because the maximal chain determines the entire set. That's the theorem. So we are going to take maximal chains and we are going to build some graphs out of it. And there is this beautiful way to do it, which is due to not a gas, but there is this beautiful bijection between maximal change in the Weak Bruhat order and tableaus, which are just boxes of a staircase shape. All that means is put one box, after that put two boxes, after that put three boxes, after that put four boxes, after that put five boxes.